Some of the biggest breakthroughs in math didn't come from finding a solution that was already there. Nope. They came from having the guts to invent a new one. Today, we're going to dive into the story of how a seemingly impossible problem led to a whole new dimension of numbers.
So let me ask you this. How do you solve the unsolvable? For centuries, this very question was a brick wall for mathematicians when they ran into certain kinds of equations.
Okay, check this out. X squared plus 9 equals 0. Looks pretty harmless, right? You'd think a basic algebra problem like this would have a simple, straightforward answer. But watch what happens. As soon as we rearrange it, we get x squared equals -9. And boom, we've hit a wall. Think about it. What number, when you multiply it by itself, gives you a negative? A positive times a positive is positive. A negative times a negative is also positive. With the numbers we use every day, there's just no answer. And you can actually see the problem if you graph it. If we plot y equals x squared plus 9, the solutions are supposed to be where the curve hits that horizontal x-axis. But look, this parabola just floats. It never touches down. In the world of what we call real numbers, there's just no solution to be found. So yeah, that right there, that's the parabola's problem. It's a huge, glaring sign that the good old number line we're all used to, it just isn't enough to tell the whole story. So what did mathematicians do? Did they just give up? No way. They did something brilliant, something a little bit crazy. They decided that if the number they needed didn't exist, well, then they just have to invent it. And here it is. Meet the hero of our story, the imaginary unit, which we call I. It's a number defined by just one elegant, rule-breaking property. I squared equals -1. That means I is the square root of -1. This one little idea, it's the key that unlocks everything. And check out how useful this thing is. Let's say we need to find the square root of -16, something that used to be impossible. Well, now we can just split it into the square root of 16 times the square root of -1. The square root of 16 is obviously 4, and we just defined the square root of -1 as I. So the answer? It's just 4i. Just like that, the impossible becomes simple. But here's where it gets really wild. Inventing I wasn't just about solving one annoying little problem. No, it allowed us to build an entire new landscape for numbers. We're all used to thinking of numbers on a single, flat, one-dimensional line, right? But I gives us a whole other dimension. It's like we've been living on a single road, and someone just showed us that there's a whole city grid. We've gone from a number line to a vast, two-dimensional complex plane. And this is what we call a complex number. It's any number that looks like a plus bi. The a part is the real part that tells you how far to walk left or right on our map. And the b part is the imaginary part, which tells you how far to go up or down. So when you plot these numbers on what's called an Argand diagram, every single complex number has its own unique address, its own specific point on the plane. You've got the familiar real axis running horizontal, and now this brand new imaginary axis running vertical. It's a complete map of this incredible new world of numbers. And in this new world, a really beautiful symmetry starts to show up. It's called the complex conjugate root theorem. And it basically says that for most polynomials, these complex roots never show up alone. If a plus bi is a solution, then its mirror image, a minus bi, has to be a solution too. They're like buddies. They always come in pairs. All right, we've got our new tool, we've got our map. Let's go back and finally tackle those equations that we used to think were unsolvable. And our weapon of choice? An old friend from algebra class, the quadratic formula. This thing is the powerhouse designed to solve any quadratic equation you can throw at it. Of course, there was always that one catch, right? That part under the square root, the discriminant. We were always told that if that number turned out negative, you just stop. Game over. No real solution. Well, that roadblock is about to get demolished. Let's walk through one. Take the equation x squared minus 4x plus 7 equals 0. We plug the values into the formula, we simplify, and yep, there it is. The discriminant is the square root of -12. Before I, this was a dead end. But now, it's no problem. We just rewrite it as 2i times the square root of 3, and the formula just keeps on working. And would you look at that?
our supposedly unsolvable equation has two perfectly valid complex solutions, 2 plus I times the square root of 3, and its partner, 2 minus I times the square root of 3. A perfect conjugate pair, exactly like the theorem said there would be. But the story gets even bigger. This invention, this number I, didn't just fix a few equations. It pulled back the curtain on something huge, something fundamental about the very nature of algebra itself.
This, right here, is the fundamental theorem of algebra. And I am not exaggerating when I say it's one of the most elegant and powerful truths in all of mathematics. It states that every single polynomial equation has at least one solution, as long as you're looking in the world of complex numbers. So what does that really mean? It means a polynomial of degree n will have exactly n roots. A quadratic, a second-degree polynomial, it'll always have 2 roots. A cubic will always have 3. A fifth-degree polynomial will have 5. Always. No more exceptions, no more dead ends. With complex numbers, the system is finally complete.
I mean, just think about that journey for a second. What started out as a clever little hack to get around a negative sign under a square root turned out to be the missing piece of the puzzle, a universal key that unlocked the entire beautiful structure of algebra. And all of this leaves us with one last big question to chew on. If these so-called imaginary numbers are absolutely essential for solving real-world problems in physics, in electronics, in engineering, then just how imaginary are they really?